AY24S2 Test, FA, Paper 1 Question 4. This question models the motion of a piston in the x direction, with second-order differential equation. It is required to solve for x of t, describing the position of the piston, from the differential equation, using Laplace transform. First, substitute all the constants with numerical values and the expression of supply pressure, in the differential equation. Now, calculate all the numerical values to get just integers. If the coefficients do not reduce to whole numbers, keep them as fractions and not as decimals. Now, reduce the coefficients further. In this case, divide both sides of the equation by 2. Now, perform Laplace transform of both sides of the equation. Refer to the list of transforms in the formula list. Then substitute the values for the initial condition, when t equals 0. Now, when t equals 0, x is 2, and the piston is stationary, hence the speed, or x prime, is 0. Calculate all numerical coefficients, keeping them as fractions and not as decimal values. Manipulate the terms, with the aim of getting big X of s on the left side, and the rest, in the s domain, on the right side. Whenever possible, simplify the expression of the right side, by bringing out any common factor of the terms. In this case, there is a factor of 2. So now it is necessary to break up the RHS of the equation into separate fractional terms, such that inverse Laplace transforms exist for each of the terms. To do this, just look at the denominator of the expression. There are 3 terms: s squared plus 4, s plus 6, and s plus 10. So this expression can be expanded into 3 partial fractions. It would be necessary to use partial fraction methods to obtain the appropriate fractional terms. For the first fraction with denominator, s squared plus 4, the numerator will be in the form as plus b. The second fraction will just have a numerical variable, c, as the numerator. And the third fraction will also just have a numerical variable d, as the numerator. Now combine the 4 terms on the right-hand side, to obtain a single rational term. Now, equate the numerator on either side of the equation. And it is now possible to solve for the 4 unknowns, a, b, c and d. Examining the right-hand side of the equation, to check for easy way to solve for the unknowns. To solve for c, let s be equal to -6. Substitute for s in the equation. This gives 416 on the left-hand side, and 160c on the right. Hence, c equals 416 over 160. Which is simplified to 52 over 20, then to 13 over 5. Remember to keep this value as a fraction, and not a decimal value. To solve for d, let s be equal to -10. Substitute for s in the equation. This gives 640 on the left-hand side, and -416d on the right. Hence, d equals -640 over 416. Which is simplified to -80 over 52, then to -20 over 13. Knowing the values of c and d, it is now possible to solve for b, by letting s be equal to 0. Substitute for s in the equation. This immediately gives 80 on the left-hand side. On the right, it gives 60b plus 40c plus 24d. Reduce the equation by dividing either side of the equation by 4. This gives 20 on the left side of the equation, and on the right, it gives 15b plus 10c plus 6d. Substitute c and d with their actual values. 13 over 5 for c, and -20 over 13 for d. Work on the arithmetic step by step. Finally, getting 15b equals to 42 over 13. Simplify further, to get 5b equals to 14 over 13. Then b equals to 14 over 65. Now, with known values for b, c and d, it is possible to solve for a. Let s be equal to 1. Substitute for s in the equation. Giving 101 on the left side of the equation, and on the right side, 77a plus 77b plus 55c plus 35d. Now substitute b, c and d with their actual values. The right side now equals to 77a plus 1078 over 65 plus 143 minus 700 over 13. Simplify and move the terms. to finally get 77a equals minus 308 over 65. Simplify further to give a equals minus 4 over 65. With the values of a, b, c and d, it is now possible to write the right-hand side of the S-domain expression with 4 terms upon which inverse Laplace transform can be applied. Substitute the unknowns a, b, c and d, with their numerical values. Split the first term into 2 fractions, so that each term will have an inverse Laplace transform. Apply the inverse Laplace transform for every term. So that x of t now equals minus 8 over 65 cosine 2t plus 14 over 65 sine 2t, plus 26 over 5 e to the power of minus 6t, minus 40 over 13 e to the power of minus 10t. The coefficients of the 4 terms can be left as fractions, or calculated to give decimal values. Finally, it is required to provide the steady-state motion, or displacement, of the piston, that is when t becomes very large. When t becomes very large, that is, t tends to infinity, the term, e to the power of minus 6t, tends to 0, and the term, e to the power of minus 10t, also tends to 0. And so, x of t is left with a sine function and a cosine function. This describes an oscillatory motion.